We have with us three very interesting speakers today that I'd like to introduce. Starting with myself, I'm currently with the managing principal of Jacobs, which is a very large firm in the United States, and I'm the managing principal of architecture and design. For me, that's a very interesting opportunity to take a long history of my career in high-rise buildings and see if I can't get my arms around a larger firm to apply it to exactly the same issues we're all focusing on here in Mumbai. The first speaker is Russell Gilchrist of Skidmore Owings Merrill in Chicago, and he will be speaking on sustainable strategies for high-rise buildings. Please welcome Russell Gilchrist.
Thank you. My presentation is actually in two parts. The first part, I'm going to show you some projects that we've been working on, high-rise buildings, and show you some opportunities that we were trying to exploit by virtue of having a high-rise building to design. The second part of the presentation is more of a case study, and it's one that's under construction that attempts to pull together some or if not all of the aspects in the preceding four projects. So this is a mixed-use tower in Korea. It's a project that's been engineered in SOM Chicago, but our New York group in terms of are doing the architecture. You know, as architects and designers and engineers, we spend a lot of our time trying to keep out the elements. Some of the things that you're going to see today are actually trying to tap into some of these free passive energy streams and maybe put them to good use. So the diagram up on the screen is really taking maybe a more conventional approach to high-rise design and looking at a slightly different way. So, and also trying to understand, you know, what natural effects and what natural phenomena could maybe aid or assist the design. What we've actually developed is the idea of a solar chimney. The idea that we're trying to induce some stack effect within the building to actually maybe generate some wind energy via wind turbines, both at the base of the building and maybe the top of the building. And bring together the idea that maybe in certain aspects of the building, rather than trying to keep the solar gains out, we might want to actually encourage them to try and induce the stack effect to maximum advantage using different glass types. There's some CFD analysis of our in-house MEP group in Chicago, and also we have a sustainability group in the Chicago office too. So we're doing all of this analysis mostly in-house. Some of the stuff that you'll see on Pearl River Tower, actually Peter Irwin and his group actually assisted us with. And it's really the idea of taking a mixed-use tower. At the lower level, we've got a hotel component and some office component, and a residential service apartment component at the top. And really what we're trying to do is to bring in the air at a lower level. Actually, Korea is actually a reasonably good climate during mid-season to actually naturally ventilate the building. At those times, we're probably not talking about very high wind speed necessarily, so the two are not necessarily acting in tandem. But during the blowier months of the year, then we're going to try and optimize some of this wind energy, both at the base of the building by drawing air in and using some of that air to naturally ventilate some of the upper apartment buildings, and also trying to harness it for wind energy, for electrical power. This is just a little section showing you some of the residential areas and how we might naturally ventilate the main atrium building. I'm going to talk about this in a little bit more detail in some of the other buildings. So I'm just going to take you through, because I've got rather a lot of slides, and I'll just race through them. The other thing that we're trying to penetrate into this building, which is obviously a reasonably tall building, it's 400 or 500 meters, is try to bring in the natural light into the building as much as possible, particularly for the apartment buildings. The apartment buildings are actually single aspect, so it's the circulation areas to the apartments that we're concentrating on, trying to bring light down. And obviously like the atrium building, atrium portion of the hotel. So this is just a quick diagram to try to bring together all the three concepts of bringing fresh air into the building and maybe harnessing it for power and actually trying to bring natural ventilation, natural light into the base of the building as well. Given that we've just opened Burj Khalifa, as it's now known, a month or so ago, I thought it was only appropriate that we put the tallest building in the world at the Council for Tall Buildings Conference. So here we are. So apart from having a rather large amount of area in a building, there are one or two aspects of this that are actually quite interesting from trying to harness some opportunities that are a function of actually having a very, very tall building. Some of these are not necessarily particular to obviously a high-rise condition. They could easily be a lower building or even a low-rise building. Some of the issues in terms of how one generates or gets electricity to flow through a building are obviously more of a challenge in a high-rise building in terms of voltage drops and the like. But one of the particularly interesting aspects of something like Burj is the temperature of the air. It's something that is so tall is actually a lot cooler than the temperature at ground level. So one of the big ideas in Burj was actually trying to source the ventilation air from the highest point possible so that we could actually take advantage of that cooler air to bring it into the building as our fresh air supply so that we're not having to spend energy bringing it in at the lower levels to cool it further. It's sort of complete with some of the normal energy recovery systems that you might find on a building of a lower size. One of the other interesting things with the Burj is obviously the stack effect of a building that's so tall. Now we spend a lot of time and effort trying to control the stack effect through the elevator shafts and the like, risers, by having a series of lobby areas rather than trying to deal with it in an expensive mechanical way. We try to do it in a more passive way. One of the other big aspects of a building of this size is actually the idea, is particularly in a very warm climate, where we can get temperatures of 40 or 45 degrees C, is the ability to kind of harness any water that we've got. And the size of the Burj is such that the condensate return would fill 14 Olympic-sized swimming pools during the course of a year. That's a reasonably significant amount of water, so the idea is that we're capturing that and using that. Now, this is also a project that we're working on in Shanghai, and it's called, it's on the North Bund, White Magnolia Plaza. It's actually a mixed-use development. The tall tower is actually an office building, and the other two buildings are actually hotels. So there's a kind of diversity of use in terms of peak demand in the morning and the evening from the hotel component, and obviously the daytime demand, particularly cooling load of the main building, the tall tower, which is entirely office with some amenity levels. Now, the interesting feature that we're looking at in this particular instance is the idea of using ice storage to actually saw off the peak, if you like, of the peak loading for cooling. And the idea behind this is that although China actually only has a kind of general tariff for electricity at the moment, they are moving to a point where they are going to have peak electricity periods. And so obviously we'd like to do most of the cooling when electricity is cheaper in the evening and not during the day. And the idea is that we needn't size all our chilling equipment for optimum peak load. We can actually put in smaller equipment and have the ice storage being made at night, and the ice melts during the day, and that gives us some cooling capacity. There's just a couple of schematics to show you that. We've also, this is actually a competition that we did in the Middle East, very tall building, mixed-use building. And I got ideas similar to the first building I showed you, in Seoul, DMC Tower. However, this one, because of the temperatures, this is dealing with daytime temperatures of 40 to 45 degrees, we get an interesting stack effect if we introduce air at the atrium. There's a number of other sustainable strategies which I'm going to pick up in the Pearl River Tower presentation, but the idea behind this is really, how does one cope from an air conditioning point of view, in a location where you can get temperatures of 45, 48 degrees C, and tricky humidity too. And the kind of yellow or brown patches where we want to be for comfort, and you can see we're way outside that target in terms of the prevailing conditions. So lots of CFD work in-house from our MEP team, the sustainable team. And really drawing on the aspect of, again, from Burj, if you like, where we have the cooler air at the top, the idea that we can draw in that cooler air at the top, and it would obviously drop because it's cooler than the air in terms of in the atrium. And depending on the time of year, we can ventilate some of the apartment buildings through ventilation, and equally, we can actually let that air escape at the lower level and actually drive the turbines too. The reason it's capped there is that we have a hotel component that has a sealed lid. Now, as the temperature heats up, you can see that it's pointless actually trying to ventilate the apartments because the air would be too warm to provide you with any reasonable natural ventilation. So really all we're doing in that condition is really using the atrium as a reverse chimney, and again, we have wind turbines at the lower level that can actually pick up some of this excess air movement. Now, it does get to a point during the day when it actually gets so hot that there is really no point trying to bring that air into the building at all. And that's really what this diagram is trying to show you. And then we actually get some times of the day or year where we get a mixed mode, where actually we can draw the air in, and in certain parts of the atria or the void, it would actually rise, and actually certain parts of the building would actually drop because that air at midpoint or higher up the building would actually be cooler than the air in the lower part of the atrium. So kind of interesting bit of analysis really for that competition. These are some of the wind turbines that you actually see on the Pearl River Tower. We're also proposing that we had solar heating on the pinnacle, because the top part of the building is primarily housing the wind turbines and the solar thermal heating. These are just little graphics showing you how the air would give you through ventilation in some of the apartment buildings. Those times of the year where it was mixed, mid-season, where we could actually draw the air in. That's obviously just a normal conditioning mode. That's actually drawing air from the cooler air from the atrium, and the times that we can do that. And that's actually the office component, which actually has a radiant chilled ceiling in it. Also, lots of studies. This was a competition entry, just facade studies trying to analyze solar gain impact on the facade system and how one might moderate that, both in terms of angle of glass and also what solar fin protection we might need to protect it further. And albeit this was a competition, we were actually starting to see some reasonable savings in terms of what this approach might actually derive. So 16% in energy savings and 34% potential in terms of energy generation. And again, being the Middle East, there was obviously a strategy in terms of trying to minimize the use of any wastewater. Also, I think one interesting thing about sustainability is not just necessarily about the systems, it's actually trying to cultivate a design or approach to structure and other disciplines that might actually look at material energy and optimizing structures to such a point that we can maybe use less material. Bill Baker can field any tricky questions on us a bit later. But you can see that it's a very simple structure. We've got a kind of ring of concrete that's obviously a varying radius. And the idea here was actually to provide a structure that's basically the slab is really essentially cantilevering off that ring. So in terms of apartment layouts, when we get a tapering floor plan, we're not hindered by column positions that we often are, and flat layouts and columns ending up in cupboards and all sorts of things. And obviously gives you flexibility in terms of how one might use that space. And we did a little bit of analysis there to show that although this tower would be taller, it might use less concrete than the Burj. This is Pearl River Tower. It's a project that's actually under construction in Guangzhou. We won this project as a competition about 4 years ago. The initial idea was actually to try and design a building that would actually be net positive in terms of it would generate, well, it would not rely on the grid for electricity, and that it would actually generate some surplus energy. Now, I'm going to go through a number of strategies with you here that we employed on Pearl River Tower, and some of these strategies we didn't actually manage to achieve for very good practical reasons. And to a certain extent, that's not really the point. It's actually interesting to see how ideas, particularly at a competition level, can be generated, and how, as designers and engineers, one controls or otherwise the kind of design development of these ideas and makes them real or not. So one of the key things in terms of the shape of the building was, it was to try and give the form of the building some level of performance rather than maybe a fairly arbitrary nature. And a lot of this kind of revolved around some ideas about wind generation particularly. We'll talk about that in a moment, but I think, there are other industries that are slightly ahead of the architecture or construction industry. There's the car manufacturing and aviation that spend a lot of time on research and development, trying to optimize the shape and form of their product, whether it's to do with increased performance in terms of whether that be speed, or, whether it's to do more with having as light an object as possible so that you don't spend so much on aviation fuel. But architecture's tended to fall behind a little in that regard. So in the very beginning, we had a number of strategies, some of them passive, some of them active. But behind all of this was a kind of four-pronged approach, really, in terms of how one might achieve or realize some of these ideas. And really it's kind of captured in this diagram behind me, which is really about reduction, reclamation, absorption, and the holy grail, I guess, in generation. I'm going to briefly go through these, because they're fairly self-explanatory. I'm not going to go through the list, but one of the big kind of shifts for us was really trying to get away from an air-conditioned building as such. And really this was a kind of exploration in terms of how effective a radiant chilled ceiling system might be in a building that's 2.2 million square feet, which is the office building. It's 310 meters tall. It's under construction. It will be the largest radiant chilled ceiling ever installed. But there's a number of other kind of efficient approaches in terms of, demand-based ventilation rather than systems just running. That does tend to put a lot of emphasis on controls, which it's always a balance in terms of how one might approach these things and, God forbid, actually persuade your client to come up with the extra capital cost that one might be involved in trying to realize these things. Because I think one thing that we can all be very clear of is that some of these strategies that we're approaching on this building or achieving on this building actually do attract a premium, and we can talk about that a little bit later. reclamation. That's really just an attitude about trying to squeeze every ounce of energy out of the building that we possibly can. If we're bringing an energy stream in, how can we reuse it if necessary to optimum effect? Passive absorption, this is obviously things like wind turbines, PVs, geothermal, all these free energy streams that we have at our disposal, 365 days a year, and also available when the building is not in use or primarily not in use. And again, as I mentioned earlier, microturbines. There is a statistic that from every coal-fired power station, to light a 100-watt bulb or lamp in a room, it actually takes 1,000 watts of energy from the source. Such is the nature of the inefficiency of the grid based on the coal-fired power stations, is that the inefficiencies are anywhere between 70 and 90% lost through the grid. So the idea behind the microturbines was to actually have our own power station, a series of microturbines in the basement. Now, these can be fueled in a number of different ways, whether it's biomass or methane. In our case, we're actually going to be using natural gas. Now, it's still a fossil fuel, but the efficiency of something like that using natural gas is more like 80% rather than 10 to 20%. So you can see that there's some definite benefits of using that system. Now, we weren't actually able to persuade the client to go for the microturbines. That's really partly a function. The microturbines would be the power source. They were also the mechanism by which we were going to be able to store any excess energy. So when the wind was blowing and the building wasn't in use, or the photovoltaics, the sun was hitting the building, and it was the weekend or whatever, any surplus energy would have been stored via battery and given back to the grid. Now, unfortunately, in China, there is no mechanism by which one can return, for commercial buildings at least, to return that surplus energy to the grid. And this is pretty expensive equipment. So in terms of just pure economics, that wasn't really something the client wanted to actually undertake at this point, because the capital cost of such an installation is reasonably high. However, we have managed to persuade him to keep space in the building, and there was space allocated in the first instance so that we could retrofit it at a later date. I mean, obviously it would be slightly more expensive installation, but that's still something we're keeping at the back of our minds, because it won't be long before China does have an infrastructure system that will allow all sorts of buildings to be able to give any surplus energy back to the grid. It's very prevalent in Europe. In France, they'll give you 2.7, 2.8 times the unit cost back if you actually return energy back to the utility company. So it is a worthwhile exercise if one can do it. Just a little bit of background about where Pearl River Tower is. It's in Guangzhou. It is a primary city in China. It's got a population greater than London. So if you haven't heard of it, it's a pretty big city. It is a humid climate, and I've no doubt if we've got any engineers in here, I'll have some questions about how the radiant chilled ceiling works with that, but I'll attempt to head some of those questions off before we get there. This is Guangzhou, and this is our site. It's just to the east of the existing town. There's a whole master plan. There's a number of tall buildings. The Guangzhou TV tower, you may have seen, is a very, very tall building. It's 400 or 500 meters tall. There's several other high-rise buildings taller than Pearl under construction. And it's all master planned around a huge, big park. The little red diagram on the top left of the site plan there is our building. And we're situated immediately adjacent to the park. And we'll talk about the wind turbines in a moment, but the adjacent, no buildings can be built directly in front of Pearl River under the current master plan. And the adjacent buildings are all less than 90 meters, which is way below our wind turbine height anyway. So you can see the little graphic there with the sun path is, because of its proximity to the equator, the solar path in summer particularly is almost directly overhead. Our issues actually are solar gains in the winter actually, so to the extent that they exist. What we tried to do to measure the performance of Pearl and how we were going to try and, albeit not get to zero energy or net positive, we adopted a kind of base model to try and measure the performance of all these various systems that I'm going to take you through. And we estimated that over the lifetime of the building, which I think we put at 120 years, we were going to emit 21 billion pounds of CO2. So sounds like rather a lot. So that was really our goal. And that was really based on a Chinese code-compliant building of a similar size and similar height. So what would pass the Chinese code would be this building, potentially. So really our goal was to see how we might erode those carbon emissions, and because that's obviously a major factor, and as well as energy performance. So I'm going to take you through a little tour of how we managed to try to have some impact on that. I mentioned earlier that we're really more concerned with performance rather than form. I'll talk a little bit more about the shape of the building and the form of the building when we get onto the wind turbines in a moment, but you can see from this graphic here that lots of radiation studies, solar radiation studies, to try and identify where the optimum place to put PVs on the building might be. So that's just a little graphic. And obviously the crown of the building, the one part of the building that's exposed to probably the most solar gains, particularly in the summer months, where the sun is more or less directly overhead, seemed an opportune place to put it. Now, we got ourselves into a little bit of trouble with the client because it's kind of a function you find out when you're working in countries that maybe you're less familiar with. That was deemed by the client to be a black cap on the building, which was not very good feng shui. So we've had to cut back on the PVs on the top of the roof. We still have them there because they were adamant that we should, because it was our original design, that we should have some PVs on the roof, and they understood the logic. But we've got a very, very thin strip on the very top of the crown, rather than the full extent as shown there. And obviously the areas, if you recall back to the diagram that you saw a couple of slides ago, obviously the areas where the wind turbine areas where the building starts to curve in are obviously prime areas for optimizing solar gains. And I'll talk about the facade system on the north and south in a moment. We have a different system on the east and west where we have a triple glazed facade, but we have effectively a brise soleil on the east and west facades. Oh, better hurry up. That's thrown me. We have a brise soleil, and sorry, on the leading edge of the brise soleil, we actually have PVs as well. So they're going to be very exposed to solar gains in the morning and the afternoon. I'll flick through this. Obviously, when you've got a glazed office building, as this is, tall building, there's always this dilemma between how you harness natural daylight and minimize the use of artificial light and deal with the solar gains as well. That's the office areas. The other slide was the lobby areas. I'm going to have to be very quick here. Can I do what the shuttering guy did and just have 3 more minutes and then 3 more minutes after that? Okay. I'm just going to take you through some brief analysis of the wind, because obviously that's a key factor. The building shape in plan is too curved on the long edges. And we've got relatively sharp, short, straight east and west elevations. Now, what that does, because the building actually sits in the prevailing wind, it's the prevailing wind for 10.5 months of the year is from the south. So we're capturing head-on that wind power. We're employing vertical axis wind turbines. That's not the horizontal ones that you see in fields at 150-meter blade size. These are vertical axis. Now, what happens is that the shape of the building actually builds up a negative pressure on the leeward side of the building. So in effect, what happens is that when the approaching wind comes and that negative pressure builds up, it actually pulls and sucks through the wind through those 4 apertures in the building. And what's interesting, and it's a while since I did physics at high school, but that equation is actually a function of that prevailing wind is actually a cube root through those apertures. So even relatively benign winds of 2-3 meters a second you're getting 8 meters a second or 27 meters a second. So you can see that even relatively benign low winds, you can actually generate a lot of power through the openings. This is just a quick graphic that shows you wind tunnel testing, which I'm not going to do because Peter will probably talk a little bit about that in a moment. We analyzed the building and the wind tunnel test, obviously for structural reasons, but also to see the performance through the wind turbine areas. And this is the approaching wind, and this is the wind that we actually get through those apertures. So this is the wind that the wind turbines are seeing. On the lower level, too, which are 100 meters up or 110 and 220, you'd obviously expect lower approaching winds because the wind speed, the lower you get to the ground level, the lower the wind speed. So, but actually what we were surprised to see was actually the wind speed through those areas was actually almost as good as the wind at the upper levels. These are just some graphics that I think Peter was involved in actually at some point. This is just showing you the apertures. The wind turbines are located by the mechanical plant rooms. We were worried in the beginning that they might be noisy and they might vibrate, but actually we've been assured by Windside, who are actually going to be installing these turbines in the building, that actually the noise that's generated is lower than the background hum of the mechanical plant in the adjoining areas. This is just a little graphic that shows you when the wind blows, we get battery power. We could store that and use it. Those were the micro turbines that we weren't able to use. This is obviously what we're all about. We're trying to create a building that people are going to spend large parts of their life in. We're using a radiant chilled ceiling. I'm going to have to skip through. The radiant chilled ceiling is working with floor-fed ventilation. Now, we do have air in the building, but it's supply air only. We're not relying on that air to cool the building. The floor-fed ventilation, the radiant chilled ceiling, and the exterior wall are all working together. And what we're trying to do with the solar gains that are coming from the south is trying to trap them in a cavity. We have a double wall system, internally ventilated facade system that has a mechanically operated blind in there. We're trapping that air in there, we're extracting it up at high level, and we're either exhausting it or we're using it as a preheat or pre-cool depending on the time of year. These things together are trying to contour the air temperature so that we get an even air temperature, even up to and adjacent to the glazed area. The glass surface will be reasonably warm. We think it's going to be anything up to 83 degrees Fahrenheit, but it's still easy to work next to it. The facade I can take questions on. It's a double wall system. Our problem is not in the summer months because the sun is directly overhead. It's November the 11th or some such day. Humidity is an issue. I'm going to have to pick this up in questions if anybody has some, but we've got ways and means of dealing with that. Now, the 4 strategies that I gave you, these are some of the systems that we employed in terms of the generation, reclamation, and such like. Now, we couldn't do some of them. We couldn't do the geothermal. We couldn't do the microturbines. The water temperature was too warm for us to be of any use to us. The microturbines I've explained. Now, what we got to is, rather than that 21 billion, we're at a more respectable 8 or just under 9 billion. It seems like quite a lot, but it does represent quite a reduction in terms of all of these strategies working together. And it really is the combination of all these working together. You cannot use the double wall in isolation because it'll have an effect on all the other systems. We're always criticized for how much a double wall might cost, but when you factor it into the size of the mechanical systems, it starts to pay for itself. Just a quick last one, because if we've got any developers in the room, they'll be interested in this. It's all very well having these ideas. I will literally be a minute, Richard. This is a little graphic that shows you the cooling, the reduced cooling, the reduced pumps and fans, because we've got very little in the way of air handling units, and the reduced lighting load. Now, one big thing was this allowed us, this technique of using the radiant chilled ceiling, the floor-fed ventilation, allowed us to have a 3.9 floor-to-floor height, rather than a 4.2, 4.5 typically in an all-air system. This saved 21 meters in the building. This allowed us to get another 5 floors of free area, effectively, within the planning permission. We also benchmarked it against other cores. Because we're using water, chilled water, rather than air to cool the building, our riser size were much smaller. So we are 8% smaller than an all-air building. So that increases the efficiency of the floor area to support area. And we did a little back-of-the-envelope kind of calculation that all these systems, and I mentioned earlier there is a capital cost, we believe that we could get that money back within 5 years. So the interesting thing about this is that actually a lot of these systems actually just make good business sense, as well as optimizing comfort and energy reduction. Just some last shots of a visual mock-up of the double wall that we visited last November. This was a building as photographed about a week ago. It's a real building, it's under construction, and it's due to finish on the 10th of October. This is a quote by one of the founding partners, which you may recall, Richard, 40 years ago. It's probably more appropriate now than it was when he first said it. That's the presentation.